Good morning, everybody, and welcome to this 14th International HCH and Pesticides Forum. This
forum has been organized within the life surfing framework. It is coordinated by the Government of Aragon, and this first session is therefore devoted to the project. Life surfing has been a landmark for Aragon because it is the solution to a very serious problem that we have in our sites, linden contaminated sites, as is the dense phase. This has been a project where a pilot project has been carried out. I am Elena Cano, the Chief of Service of Contaminated Soils in the Government of Aragon. I'm going to moderate this session together with Jorge Net, who is the Chief of Linden Contaminated Soils section of the Government of Aragon. In the first part, we're going to focus on the preparatory actions and the first phase of the action plan. I am going to invite the speakers of the first presentations, the four first presentations, to come here. Jorge Net, who I just introduced. If you can please sit here. Alicia Sanchez-Valverde, the Manager of European Projects, the environmental section of the Government of Aragon, in Sarga, I mean, and Jesus Mendez, a geologist of the Government of Aragon from the Contaminated Soils Department of the Government of Aragon as well. You can come here. I remind you all that you have 15 minutes for your presentation. Please be punctual, and I'll remind you about the time when a couple of minutes are still to go. And please do not rush when speaking to facilitate the interpretation. And then we will, after the presentations, we will make a Q&A session or a roundtable with Q&As, and then we will have the coffee break. So, Jorge Net Ortega, the floor is yours. Thank you very much, Elena. First of all, good morning. I would like to welcome you and thank you for your coming here, both in person and remotely. As Elena was saying, this forum is the result of one of the actions of the life surfing project, and we considered that it would be a good idea to start with this presentation to give you some context on what we're talking about. I'm going to give a general vision, a non-technical vision, because this will be tackled by my colleagues, on why this project was born, what is it about, and what are the goals. First of all, we need to locate ourselves geographically. The life surfing project is developed in the Bailin landfill, which is located in a small municipality called Sabiñánigo at the north of Aragon and close to the Pyrenees. As you can see here, in a very reduced space, we have three currently active contamination sites: the Linden manufacturing plant, the Sardas dumpfill or landfill, and the Bailin landfill. In between of the three sites, there's the Gallego River flowing. We're talking about Linden. What is Linden? Linden is the gamma hexachlorocyclohexane, shortly for HCH. This was used at the beginning of the 90s as pesticide in the agricultural sector, as well as for the treatment of parasites in cattle, or for the treatment of louses and lice, or scabies in human beings. It has been prohibited according to the Stockholm Convention on Persistent Organic and Pollutants in 2009. And as a relevant piece of data that is going to be very significant for this problem, I would like to say that Linden production is a very inefficient process, since for the making of 1 kilo of commercial production, 9 kilos of waste are created or produced. Due to failure in the reactions or the distillation, there is a large liquid part, chlorinated organic compounds, as what we call the DNAPL, which is the dense non-aqueous phase liquids produced in failed reactions and distillation tails. And we also have solid waste, such as other HCH isomers, but the liquid phase is the problem, really. The problem started in the old Inquinosa factory or manufacturing plant that was producing in Lindane from 1975 to 1992. That company dumped in an uncontrolled way the waste in the Sardas landfill, and then when it filled up between 1983 and 1995, it dumped the 65,000 tons and 1,400 cubic meters of DNAPL in the other landfill, which is the Bailín landfill. All this waste was dumped in an uncontrolled way because this old dumpfill or landfill was isolated. It didn't have any leachate capturing mechanism, and it was less than 400 meters from the Gallego River, and therefore less than one kilometer, really less than 1,000 meters from the Gallego River. So we decided to take the solid waste to a nearby dump, but although in the old dump there is no solid waste, the liquid phase or the liquid waste was already present in the fractures. As the Gallego River was very close by, there was a problem, and we had to continue working, removing waste, liquid waste in this case. In order for you to understand the problem a bit better, we need to speak about the geology of the aquifer in a specific way. The old Bailín landfill is composed by an alternance of sandstones and siltstone layers. The first ones are permeable, but the siltstones are not permeable. I mean that they cannot let water go through, and they are waterproof, really. And there is a high risk, therefore, in the M layer, what we call the M layer that you can see here. Due to this connection, there is a high contamination risk to the Gallego River. And this is why we need to act. We needed to act. Apart from the transfer of the materials in the 90s, some purification or water treatment plants were installed. There was some leachate and network of piezometers. Monitoring the plume was established, which also was useful for us to establish a pumping network. In 1995, we started pumping liquid DNAPL waste. And as you can see in the graph, every year the flow extracted was less up to the current situation when the liquid pumpable waste is practically depleted. And the only thing we have there is the DNAPL, the liquid residual phase, which is accumulated in fractures, in cracks, or in cul-de-sacs. And this is why it cannot be extracted or pumped. And therefore, the waste here is still an active site And therefore, the contamination risk is still present, and we need to act further. Between 2014 and 2017, there was a live project called Life Discovered, the goal of which was to prove the feasibility of the application of chemical oxidation in situ, the ISCO. It was successful. We had a dissolved mass of HCH in underground water, but in the DNAPL, the effectiveness was minimal, and therefore we still have residual DNAPL remains in fractures. And this is why we needed to act further, and this is why the live surfing project was created. This is the full name, the SURFACTANT Enhanced Chemical Oxidation for Remediating DNAPL. And the goal of this project is to demonstrate the field feasibility and effectiveness of a soil decontamination technique in soils containing residual DNAPL of HCH residues. This is what we call ISCO, due to the acronym in English, together with a SURFACTANT, with the goal of minimizing up to the maximum the contaminant mass from the aquifer, and previously to apply bioremediation among other practices. The project was developed in Bailín, in the Bailín landfill. As you have seen, there are other sites affected by the contamination, but also in other European countries. And this is why another main goal of this project is to assess the feasibility and replicability and transferability for its application in other locations affected by the same problem. The duration is 60 months. There were some delays due to the pandemic, and this is the budget, around 2 million, co-funded by the EU in 1,182,000 euros. 82,000, so 1,182,000 euros. So the beneficiary, the coordinating beneficiary is the government of Aragon, together with associated beneficiaries such as the public company Sarga, the International HCH and Pesticides Association, or IPA, in the Netherlands, the Complutense University of Madrid, and the University of Stuttgart. This project is composed by 5 actions, and every partner participates as a responsible party of different sub-actions within every one of the blocks. I'm going to mention them because I know that we are a bit short on time. The first action block is preparatory actions, the implementation of the pilot project actions, the monitoring and follow-up of the impact that can be produced by the project. Also, public awareness and dissemination actions, and actions related to the project management itself. The main thing is the pilot test, which is framed within the actions structure, and it is structured in 3 phases. The phase 0, the preparatory tests, is a very important phase, which consisted in the making of different hydrogeological tests, such as injection and pumping or tracer tests. There was a preliminary test in the barrier zone. I need to say that the barrier zone is an area that has been placed between the injection area and the river so as to avoid non-desired leakages, and we will hear a presentation on this precisely. The goal of this phase is to acquire the greatest possible data and knowledge of the aquifer in order to design the latter phase in an optimal way and at maximum efficiency. Here you have important data such as the distribution of fracturing and its connectivity, the permeability, injection flows, the flow speed, contact time of the fluid with the contaminant, and arrival times of the tracers to the river and the barrier zone. With all this data, we established a design of the first phase of the pilot test, which is the phase 1, the SEAR, which is the remediation phase improved with SURFactants. This is the SEAR phase, which consisted on injecting surfactant with a small percentage of hydrogen peroxide into the selected piezometers, in some cases with some recirculation, and finally pumping to recover the injected material. Why? Because we wanted to solubilize the residual DNAPL and then pump it together with the contaminant mass, I mean the injected flow and the mass, and we would place the resulting mass in other locations nearby, which we also treated by alkaline hydrolysis or with active carbon or with the Fenton technique, or the Fenton treatment, sorry. And then after phase 1, there's the second phase, which is what we call enhanced in situ chemical oxidation with surfactants, or SISCO. In that phase, the second phase, we injected an oxidant, sodium persulfate with alkaline activation aided by the addition of a non-ionic surfactant. The injection is carried out in the piezometer selected by the data from the previous phase, phase 1, and the injected fluid surfactant plus oxidant is recirculated, and finally the generated front is treated in the barrier zone, the goal of which is to degrade the largest possible volume of residual dense phase, the DNAPL. Then we move on to phase 3, which is the ISCO test rebound effect evaluation, where we inject an oxidant, the ISCO test, in the piezometer selected by the data from the previous phase. And the goal of which is to evaluate the possible rebound effect, since after the different injections of SEAR and ISCO fluids in the previous phases, it is possible that there is a diffusion of the contaminants and the rebound effect occurs. So a new injection of SISCO can be or not be done depending on the importance of this effect. This is the summary of everything that I've said, and this can be applied to other treatments such as bioremediation, which is the step that is under study right now, the application and the feasibility of this bioremediation technique. Thank you very much for your attention, and I wish you a very fruitful conference. Thank you very much. Thank you very much, Jorge. Now we will give the floor to Alicia Sanchez-Valverde, who is going to present the facilities, the equipment, consumables, and resources in the text execution. So good morning. Welcome to the 14th Forum, which has been celebrated after 7 years. I would like to thank all the members of the government of Aragon for being here, and the fact that we can, other technicians, because we can hold this event on streaming. Sarga has been responsible of various tasks together, for example, the preparatory actions of the design of the pilot test, informing and consulting the stakeholders. We also had some implementation actions on the field test and full-scale application design, follow-up actions, and communication actions with outreach and awareness activities, the webpage, and we have collaborated in the management and the collaboration and in the coordination and making of this event. The live surfing project is pilot test to remediate soils. We wanted to see how to combine different techniques to eliminate the DNAPL phase that is residually existent in the aquifer. Then we will develop all the different steps carried out for the making of the test. I would like you to appreciate the dimension of all this work in terms of human resources, installations, equipments, etc., because the environment in itself is rather complex. Firstly, within the Bailin landfill, we had to conduct previous studies to select the most appropriate area that would enable the controlled test. Therefore, we undertook the revision of the previous information on hydrogeology, chemistry, etc., in the nearby areas to the Bailin landfill. Here you can see an aerial image with the Gallego River, the Bailin ravine, and the cell test, or the test cell, sorry, that was under study. According to these previous studies, and the revision of the document is already existing of all the works that had been done, the M layer was selected as the best location because it is close to the old facilities of the old landfill. The DNAPL was residually present. The layer was well connected in depth, and it had continuity to the pumping, monitoring, and injection actions. And the M layer had the possibility to create additional boreholes because we had a very good information of the preferential flow ways, and all the information was very much in detail. After the test phase to guarantee the safety against all risks, and hydrogeological study was conducted, and we had to analyze in the experimental and technical design of the test. We also analyzed the geochemical data of the selected test area, reagent dosing, laboratory tests with surfactants, and we made a review, a research review of the SEAR, the surfactant enhanced remediation, and an analysis of the SISCO, the surfactant enhanced in situ chemical oxidation. And we defined the field work with the adequacy of the different accesses, drilling of new boreholes, hydraulic tests, including pumping, injection, and tracer tests, and the design of the safety barrier. This was done by Sarga in collaboration with the government of Aragon to meet the technical requirements of the injection test and internal recirculation layer M. In parallel, the government of Aragon, together with the Complutense University of Madrid, who is another partner of the project, defined those protocols and procedures for carrying out the preliminary tests. And we finally defined a text execution protocol, including two phases. The first one, the SEAR test with surfactant enhanced extraction, consisting of 2 injection events, and the phase 2, which is the SISCO test, in situ chemical oxidation enhanced with surfactants performed in 1 injection event. In these protocols, the control and follow-up methodology of the trial was defined, including data collection and analysis in situ and in the laboratory prior to, during, and after carrying out each of the stages of the test. And this is stage 2, what we call the facilities stage or phase. Therefore, we located the injection area, the test area, and the barrier area in the area that you can see here within the square in yellow. We define these 3 areas. You see the injection area on the right-hand side, the test area, and the barrier area on the left-hand side. And the new boreholes were conducted or carried out in the lower part of the screen, as you can see the map. For the execution, it was necessary to carry out civil works we could not work unless we implemented accesses and platforms for the boreholes. It was very complex because the orography is rather complicated. Everything was planned with safety guidelines and safety guarantees so that all the works would be done in the optimum conditions. The platforms allowed for, or the concrete platforms allowed for the installation of reagents and all the different mechanisms that we had to use. You see different photos of the in situ works, in the field works. 7 new piezometers were executed from P190 to P196 that were located on layer M on the slope of the dismantled basin of the Bailin landfill. The length of the piezometers was between 30 and 45 meters deep. Here you can see more detail of the boreholes in the test cell. Once the civil works were concluded, then we included the facilities in the injection area. They were rented. These facilities were rented because we did not see any reason to leave them permanently. And in the injection area, at a distance of 200 meters and at a higher height, we implemented the feeding area where the reagents and the injections to be applied would be. We had to rent lorries, plume mechanisms as well, and we had the leachates sent by pumping. We had different equipments for the leachate with activated carbon, the Fenton treatment, and hydrolysis. These are the images of the different test areas. And this is the barrier area that constituted an area more than 100 meters, collecting the leachate from the injection zone sent by pumping. Different equipments were arranged to carry out the leachate treatments with different techniques. As I mentioned before, activated carbon, Fenton treatment, and hydrolysis. We installed more than 200 elements between reactors, manifolds, pumps, flow meters, and different density devices in different sections. To complete and facilitate the manipulation, analysis, and follow-up of all the samples, we bought or acquired a gas chromatographer with a detector to capture electrons and ionization. I think the cost was 64,000 euros, if I'm not mistaken. As for the test execution, we had all the previous studies, all the installations working in good order. And for the execution of the test, we used 10,200 kilograms and 7,700 kilos of chemical products between reagents and other chemical products. We selected the EMULSION SURFACTANT and the reagent due to the non-ionical biodegradable and low foam generation characteristics was ideal for our work. As for consumables, for the handling of chemical products and reagents, auxiliary equipment and tools have been used. Dosing and submersible pumps, packers, measurement probes, point samplers, interface and TLC measurement probes, containers, sampling tubes, bladder pumps, electrodes, manometers, and small hardware and laboratory consumables requiring continuous replacement, avoiding cross-contamination and material wear. These are some of the consumables that we used. And as for human resources, laboratory analysis, and environmental monitoring, safety and health, We conducted all the sampling manually to have a continuous follow-up of the whole procedure. And for these different entities, such as the SARGA colleagues, whom I would like to thank very especially for their collaboration, both the laboratory, the offices, and the on-the-field team, together with the Complutense University of Madrid, the government of Aragon. We were a team of some 20 people, and we were supporting all the this work apart from the activities in our daily work. There was also the collaboration of companies such as UTOP, ICOM, Sondeos Jarema, Diego Hermanos, Hydroman, and Biotechnics, etc., for the follow-up and control tasks on the field, because it was necessary, and it was necessary to create shifts daily and weekly for both injection and pumping and control and follow-up. During the injection days, we were there at 7 a.m. o'clock until Jesus would say stop. That would be maybe at midnight or 1 a.m. So it was really, really intense. Every test period was of 5 weeks. 1 week just for the preparation, 1 for tracers, the third one for the execution of tests, and 2 more for the follow-up. In general, we planned 4 teams of 3 people, each for the injection and control days due to the continuous measurements performed. And this leads us to the quantification of the samples. I still have 2 minutes. Okay, thank you. Even though the previous work started in 2020 and involved more than 500 samples, in 2022, which is where all the tests scheduled for the live surfing project were carried out, we took 40 more samples per month compared to the control that is usually carried out, which is usually between 150 and 170 samples per month. And the samples obtained in the field were analyzed in the Bailin laboratory and in the Pyrenarium laboratory, comparing their results of all the samples with analysis carried out at the Complutense University of Madrid. In parallel, we conducted monitoring on health in the control of processes, work processes, the coordination of entrepreneurial activities, etc. We use more than 500 APIs, the PPE, sorry, the personal protection equipment with masks, goggles, etc. As for the economic analysis and the conclusions, we have grouped them according to categories. The test only in terms of foreign facilities has, and not including analysis or our procedures, it has been a total cost of 621,862.55 euros. You can see the screen. And as a result, we extracted 240 kilograms of DNAPL, which equivals 12,000 cubic hectometers, more or less 48,000 Olympic pools, you can imagine. And each kilogram of residual DNAPL extracted has a cost of 2,591 euros. We need to remediate contaminated soils. The implementation of this project wouldn't have been possible without the union or the joint efforts and public resources. We calculate that every kilogram of DNAPL in surface water, we purify a volume of 50 cubic hectometers for human consumption. We need to be responsible with the environment to avoid consequences on a larger scale. And for this, it is necessary to reconsider the measures that prevent contamination and the importance of carrying out pilot tests that allow evaluating the feasibility of how to minimize the impact of those sites that are already contaminated, reducing the cost and incorporating the economic variable in the final decision. Thank you very much for your attention. Thank you very much, Alicia. Now we will give the floor to Jesus Fernández. He is going to give two presentations. The first one related to the previous tests that have been conducted on the hydrogeological behavior of the aquifer, and the second one relative to the first in situ SEAR test. You have half an hour. Thank you.
A ver, ya sé que la foto no me hace justicia. No tenía ninguna foto mejor. Siento. En fin. Bueno, ya os han comentado mis compañeros que es live surfing. A ver, como la película esta salía un poco larga, pues hemos decidido que en esta primera temporada dejarla en 3 capítulos. Voy a ir contando capítulo por capítulo. En esta primera presentación vamos a hablar de los trabajos preparatorios. Ya os han comentado que estamos ubicados en el entorno de Sabiñánigo, específicamente en el vertedero de Bailín. Como características a destacar, aparte de los volúmenes inmensos de residuos sólidos, sobre todo es la presencia de DNAPL, que es el elemento que nos condiciona la mayor parte de los trabajos de descontaminación. Y la proximidad del río Gallego. Algunas de las fotos que veis son fotos históricas. La de arriba es un momento en el que estaban vertiendo directamente de las marmitas donde recogían la fase densa al final del enriquecimiento en HCH gamma, o algún ejemplo del muestreo de fase densa en sondeos.
And the sampling of the different boreholes. Well, we have this vertical siltstone and sandstone formation with liquid waste that percolated through the sandstones. When we detected the DNAPL, it had advanced 300 meters through the landfill, and we were extracting through pumping. We started in 2005, and there are some 30,000 liters of dense phase already extracted. And we're at a situation where the pumping is really non-performant. And this has led us to think about the treatment with SURFACTANTS.
So in this first phase, there is a first laboratory and revision of information. Apart from looking for the type of reactive during the process, we wanted to see what the techniques could be used in the barrier so that the lixiviates reach the river. Then we executed the drills, the boreholes, and then on surveys, and then the different baseline of the test zone. About the DNAPL phase, we identified up to 28 organochloride compounds with the heaviest ones, penta and hexachlorocyclohexane. Hexane is around 70% of the DNAPL. Part of the work was developed in laboratory to select the surfactants. We had been working on this. We compared up to 40 mixtures. When we started live, we had selected 2 previously, Twinspan and SDS, and the University Complutense of Madrid added a new surfactant, EMULS 3. And seeing the behavior of these mixtures, particularly in alkaline environment, because we had to mix it with enhanced sulfactate with SOSA, we saw the ease of working with reactives or reactants. So we selected emuls with an added advantage. It's easily biodegradable. In order to establish the area, we first thought about the M layer upstream from the landfill, and then during the first drillings, we didn't find any DNAPL. So we selected a new area, thinking that the axis of one of the ravines, per topography and higher fracturation, we thought that we could find more percolated. Once we selected the area, we drilled and prayed for us to be lucky. Think that we are working on vertical layers. The widest is 4 meters. That's where we work. But as you will see, the area is just 1 meter. So doing vertical drillings and be really on point is not easy. In these drillings, the idea was to make boreholes with recover of samples without the need to compare, so that we can work on packers when drilling and pumping. And during the drills, there are tests for permeability, and then samples are taken for extractions with methanol, and see the possibility that there are DNAPL on these areas. And then the odor, which is one of the clearest identifiers, even though our coordinator doesn't allow us to take off our masks to smell. Here you see the difficulty in drilling in this sort of complex topography area. We did some balconies so that the operators could work. As it's normal, not everything goes fine. In the last drilling, in the last day, very last Logion test, we found that the aquifer was collapsed 10 meters. Here we are in a particularly specific area, the border of the landfill. In the 1990s, there was a cement bentonite injections that modified completely the connection and functioning from the hydrological point of view of the layers. So in one of these drillings, we might have touched one of these fractures with this mix, and it collapsed. Here you can see a lithostratigraphic profile in the area of the tests, with the areas where we were actually able to consider the presence or occurrence of DNAPL from the sample tests of rock in fracture. Here you see how we found up to 49 grams per square meter. I think that during the drillings we used water injection, so the dense phase was washed away. So this is a contaminant that was in the layer. Here is how the test area was finally done in green with a control. Length is around 50 meters, Here is the distribution of the test cell. You see a good density of drillings, and then we, in the what we call barrier zone, taking into advantage then the big number of drillings for the previous live test for oxidants. In order to design the tests, first we needed to know in detail how the hydrological behavior of the layer was. Imagine we are in a very heterogenic area, and we need to know at the level of the fracture, what is the speed of circulation, the masses circulating. In the end, it was 7 tests with different strategies of injection and pumping that could be replicated in the tests with surfactants and oxidants. Here, some examples of results with the hydrological tests. I would like to mainly point to the high speeds that we detected the modification of levels. Over 1,000 meters per day. That means the injection in less than one day could be found in the receiver, in the receiver. Now, about the conclusions of these hydrological tests, when injecting, the fill is vertical. So this liquid injected tends to fill the bases upwards. In order to reach the target elevation, to reach the DNAPL, because we have DNAPL in the vadose zone, it is necessary to inject a flow rate close to 1,000 liters per hour. And if possible, we need to use drilling medium operating in the bases. In the cell, we were able to measure the speed, the velocity, using the context of the different compounds to see how the fluid was coming inside. So the velocity is between 5 and 10 meters per hour. And we were able to get up to velocities of 200, around 200 meters per day. Now, because the response of the different levels is a pressure response, we were not able to know how the masses were moving and what the velocity was. So that's why we carried out tracer tests using bromide for mass balances and heptanol as a compound to be absorbed preferably in DNAPL phases to try to locate the areas with DNAPL, with presence of DNAPL. Here you see the type of tracer tests, up to 5. Same with the hydrological tests, combining strategies of injection and recirculation and pumping to try and get the levels that we want to achieve to get to the DNAPL in the vadose zone and have enough time of reaction. And the monitoring, as said before, basically with conductivity probes for the detection in the vertical to see where exactly the reagents are moving. These tests are always done on objective levels or target levels, not touching the water column. And then the velocity of a test that allows us to have the laboratory on site. Here you can see other examples of how the tracer tests were with the different behavior of the levels. You see, in many cases, we reached the target level around 800,000 meters, and downstream, you see the retard or delay with the different levels as we get further from the test area. Here you can see some velocities quite high because we talk about 10-15 meters per hour, so that it is not easy to control reagents there. Now about conductivity, that gives us some hints about the heights of the different compounds. You see the entry area where the conductivity was giving us more information. Then there is a mixture area and levels that are not that conductive in the drillings, and mix of entries with lixiviates in maybe upstreams or in lateral side areas. Now, considering that all the fluid coming out of the cell that was injected is going through the different drills or boreholes, and they recovered the basis initial level, we can consider that the volume is conservative, and thanks to the different analytics over time, we can carry out a mass balance. This is particularly important, mainly to know at the initial part of the barrier area, we can find whether the surfactant is working in order to stop the arrival of lixiviate. You have 15 minutes. Fantastic. Oops, we lost it. As for the conclusions, mainly the tracer gets into the start of the barrier area, reaches up to 50% of mass. The time of response is between 10 hours, more or less, when we reach the first volumes, and the peak might be around 2 days, and we can be up to 7 or 8 days seeing the pass of the plume that was injected. Other important areas was the barrier zone behavior or operation. We did a test simulating that in drilling downstream with DNAPL present, we injected the surfactant part that could be thought to reach the barrier zone, and we applied the different treatments to see the different performance. Upstream, we dosed with SOSA for an alkaline mixture with more volatile compounds, and in the barrier zone, we had 2 probes, one with aeration and caustic soda with a reinforcement at the end. Conclusions. The alkaline hydrolysis is very good performing with a very rapid transformation up to with a very efficient transformation of HCH to trichlorobenzenes, and we also see concentrations of dichlorobenzenes grow higher than those of trichlorobenzenes. Now, we also saw that it was important to have a aeration, because that also enhances the hypersulfate aeration, and the oxidation kinetics is even faster. That facilitates degradation in a shorter term. I had found the picture. Okay, the first ones are just a repetition. We are in Sabiñánigo. We have an issue, the presence of DNAPL. We are in a situation with the residual DNAPL where we can think of different techniques. In this case is second chapter, which is the use of surfactants, sorry. Let's go over this. We just talked about this, this overall geology, the distribution of vertical zones of sandstones and siltstones, with a characteristic that sandstones fracture can be up to 40 or 50 meters, and siltstones is around 7 meters, the first 7, so that when the phreatic is below those 7 meters is the aquifer of the layer of sandstones, the one that is running towards the river. Over that height, we have a communication. We try to avoid that, to avoid increasing the contamination in other layers. So you see the selection of the surfactant. We selected emuls. We said that before, and this is the scheme of the first SEAR test. This would be the profile. We injected into drills. We set 2 packers where there is a communication, a faster communication towards the downstream. So from right to left, you see the directions of flow that we detected. In the case of other borehole, we used another packer. So we just, with very low volume, we generate depression below or beneath the packer. When we remove the packer, there is then a flow that reactivates the use of reagents or the compound. So the idea is to recover as much volume as possible to avoid it to circulate towards the river with high levels of contaminants. So we carried recirculation drills downstream, and at the end, pumping to extract as much volume possible of surfactant and contaminants. So you see here the distribution along all the layer. You see how we dose SOSA at the end to hydrolyze the heaviest contaminants, because also with higher pH that destabilizes the surfactant. In the lowest area, you see the application of air and surfactant in the barrier area to degrade the contaminants reaching this area. What are the objectives? To see that we are able to reach the target level and the cell, and to be there for at least 2 hours for it to be efficient, this stabilization with the surfactants, and to extract as much as possible, and to avoid this, stop this from reaching the river, the receiver. These are the solutions: the surfactant, 20 grams per liter, bromide for recovery balances, peroxide of hydrogen, 1%. This is used to generate foam and to help the reagents. And then injection of 9.3 cubic meters. And along the layer, we applied solution in the barrier zone to alkalinize and aerate. About the monitoring is very similar in all the drilling, with fixed probes and manual probes, and conductivity fixed probes. And in this first test, as said before, we injected 9.3 cubic meters, and we recovered 7 cubic meters. Out of these 7 cubic meters, that's around 55% in mass. Consider the mix of bromide with the conductivity, and with the surfactant 29%. That gives us a clear idea that the surfactant is not conservative and is retained in the litological materials of the cell or in the receiver, or in the area of the receiver. About the levels, we were able to reach the target levels in the needed time, and we observed that the probes reduced the basis level. The use of these solutions, particularly in the case of peroxide, hydrogen peroxide, with the shocks beneath the tracker, improved the connectivity downstream. I will go faster because I will use up too much time. About levels, we saw the delay of the fluids and the evolution of the tracer In some cases, in some drillings that are particularly well communicated, we recover the basis level so that the tracer has its peak and then it goes down up to or down to the original or initial level. But in some cases, we don't recover the basis concentration. So at the time of the test, these were at a stage level that was very low. So we saw a feeling of an area that is not well communicated, so it's retained. The surfactant is retained there. You see the evolution of the layer of contaminants of the surfactant and how the heaviest contaminants behaved and the less heavy contaminants. You see how in the test cell we found the highest solubilizations. As you can see here, the peaks reached 804 grams per liter in some of the tests in downstream, both in alkaline hydrolysis and the dispersion. We lose concentrations, and we see how the surfactant practically even doesn't go over or passes through the test cells. So that gives us some tranquility because we are not going to reach higher volumes or concentrations in the barrier zone or the receiver. And you see how when the alkaline hydrolysis starts, there is a critical change in distribution of contaminants. You see how the heaviest ones are hydrolyzed, they drop, as you will see later on, they drop to even dispersion, and the lighter contaminants are the ones that are more present, apart from the fact that concentrations in general are reduced. Also in the barrier zone, you see how the COGS collapse or drop, reaching the initial situations. And we also see how the persulfate reaches by the end of the layer is not or almost disappears because we are in a carbonate environment, so we tend to neutral. So it is necessary to inject. So in some cases they were too much distance to make this. In the second test, in the CR2, is a test. It's a push and pull type test. So we used 2 boreholes where we were not going to do an efficient recirculation. So we knew that what was going to be injected was going to reach downstream. So up to the barrier zone, it's the same idea. So we injected in 2 boreholes and we extracted at the same time. In this pumping, no, this is not correct, sorry. In this borehole, we injected 6 cubic meters. We were able to recover that. In mass, it was 77% of the tracer. We see again how the surfactant has a behavior that is not conservative and in part is retained or degraded. As for levels, same situation here. We reach object or goal or target levels. We see a retard downstream, and we saw how downstream there is a filling effect. There is a relatively slow communication, and that's why we see how they end up with some meters of column more than at the beginning. About the bromide evolution, similar to the previous case. In the case of well communicated boreholes, bromide drops to the initial phase, and in others it is entramped. But that also allows us to see when exactly we reach the barrier, so that we can see if we are correctly working. About the COCs evolution, even though we used borehole 172 and borehole 171, we see an increase in downstream, because in these other two boreholes, P81 and P55, we had room for that, so to say. So surfactant was degrading down to the level of the start point, and we see this evolution of compounds as an effect of the alkaline hydrolysis. Here is downstream. We see the hypersulfate, persulfate, the same situation of need for more points to apply SOs to activate persulfate. As conclusions, at the end of the test, we carried out development or a cleansing of the boreholes, and we recovered 100 kilograms of DNAPLs, 90 as DNAPL and 10 as dissolved DNAPL. It is possible to apply SEAR in heterogeneous fractured media, but it is essential to have a previous knowledge, detailed knowledge, in order to establish the strategy of injection and recovery. Also important, it is necessary to have a guarantee of this barrier zone to avoid that the increase of contaminants due to the solution can reach the receiver media or medium. Also to sign out that this addition of hydrogen peroxide generated foams and mobilization of both DNAPL and other particles. This is the end of the second chapter then. Thank you. Okay, so for the round of questions, let's make it in 2 sections. So if you have any questions now, let's use this time, and this will be addressed to the speakers so far. So there is this microphone you can use.
Jesus, I have a question for you. The test was carried out in a very, very dry year. How would have varied the strategy in case we had high waters?
Okay, we need to take into account that this is used here, this is valuable here, this is useful here for a heterogenic, fragmented, fractured media. But in each case, we need to think of a particular strategy. So in this case, where reagents are distributed mainly in a vertical way, we really want to have the aquifer with the lower level possible. That means we will read with a pure reagent to those areas with DNAPLs or contaminants. So if we were in higher levels of water, we should have thought of more intense pumping upstream, so that we could have reached more idoneous levels. But for different situations, the strategy should have been different.
John?
Bruce,
Espera.
now you have been doing all these tests. What will be the costs
Espera.
for the complete remediations of the DNAPLs? Now we have been testing 4 years in live discovered. We have been working 4 years now in live surfing. What are the costs to remediate the DNAPL here in this area? Just to see what are the final costs. Can you calculate that?
Well, apart from the fact that it is not very good taste talking about money. Anyway, let's think that this is a pilot project. So we have done certain actions So when carrying out bigger scale systematic work, we should not repeat certain things. We should not try and so you see, this is quite an excessive cost, of course. About surfactants in the application of SEAR, the performance per 1 liter of DNAPL, it must be applied around 3.5 kilos of surfactant. So this is not reagent balance that is too high. The cost, apart from facilities and personnel, which is quite high, is the execution of drillings, because it is necessary to have an important number of drillings. Real cost, at real scale, it's still pending to do, but based on the relation of volumes, it is not too high, taking into account that when we have DNAPL, there is a problem. Because the main problem here in the sites in Sabiñánigo is these high volumes of solid residues, but the main problem that means a hazard, a risk, since the start of activity is the presence of DNAPL.
Thank you very much. Very interesting. If we have a very extended area, I will just point to it in my talk that would be later in coming days. We have about thousands hectares of POPs polluted, all types of POPs in the northeast of Iran and near Turkmenistan, cotton fields that I was there 50 years ago, about 10 years, 20 years old, all type of aldrin, dieldrin, many types were with big planes spray. Do we have to do something with those soils now? And what would be the price there? It's all POPs, you know, the cotton fields mostly it was. Not now. Now there are, but not in that extent.
But the concentrations are very high. I need to know about the concentration. Is it dispersed? Is it concentrated?
I don't know. Every time in the World Soil Day, I just left some messages there that this is the pollution, but I didn't measure it. And I don't know in what, but it was very highly polluted that time.
According to our experience, if you have solid granular contamination, you're fucked. I'm sorry to say this, but this is exactly the term. You need to really drill and try to find how to treat whatever the result of your drilling. It could be classical forms such as incineration, you know, burning up the waste, or how to enrich the contaminants as to treat it apart and treat the soils with lower concentration of contamination in a different way. You need to ask for support to biology, to nature, to life, really bacteria I'm talking about. And according to my experience, I'm totally convinced of the fact that wherever you have the contaminants, you have the bacteria able to degrade them. So listen to some of the presentations on bio, on life, that we're going to present here, because I think this is a strategy that allows you to, in every place, any place, regardless of the economic and social development of the area, you can work with a very cost-effective technology and profitable technology, but you need to look for life, for the biological solutions.
Thank you. Thank you.
Thank you, and thank you for a very interesting presentation, which was very much at the limits of my technical understanding. But My question relates to what's happening downstream. So presumably you've tested the water in the aquifer and there is DNAPL and maybe other contaminants in that water. And maybe it's coming from the aquifer into the river system as well. So these contaminants are appearing downstream. Maybe it's too early to say from your pilot project, but is this work showing reductions in the levels of contaminants that are appearing downstream? Obviously, dealing with the source of the contamination is the important thing to do, which is what you're doing. But I'm interested in knowing what the level of reductions downstream might be.
I'm not going to advance some of the presentations that later on will deal on the follow-up of a chemical quality in the flow and downstream effectively, yes. But I'm going to say that according to the tests, the concentrations in some boreholes that we drilled close to the river are similar to the ones before the tests, meaning that we don't increase the contamination at least, but having a barrier zone that will enable us to clean, oxidize, and remove the increase that we may be causing on contaminants because of the solubilization with the surfactant. This is something fundamental, essential. We need to have safety measures in place. That's absolutely true.
Good morning, Javier Samper, University of La Coruña. It was a lot of information. I couldn't digest either, okay? So, and I understand there will be other presentations later, but okay, one comment and a question, Jesus. A comment is, it's true that DNAPL is a very important issue because as long as you have DNAPL, you will have a source of contamination. But that doesn't mean you should only concentrate on DNAPL, okay? This is something that we also see in Sardas, okay? So the problem is you have to look at the site in entire and looking at downstream. So my question was aligned to the previous one. What is going on? Okay, what are the effects, the benefits at the point where the aquifer discharges into the river? Now, you partly answered that question, but okay, it wasn't clear to me when you mentioned this zone, the barrier zone. Okay, this is what kind of barrier? Is it hydraulic barrier? Is it a chemical barrier? So what are you planning to do to prevent that when you do this testing, you don't add additional pollution to the river? So you are going to do chemical barrier or hydraulic barrier? I mean, pumping. Why not pumping and then you prevent the contaminant to go to the river? So contention. Okay, that was mine.
In our case, the barrier that we used is a physical-chemical barrier because we used aeration and vapor extraction combined with oxidation by persulfate in an alkaline medium. And we will see how we have improved in the following test, combining in the same borehole aeration with heating and oxidation with persulfate. What we achieve with this is a faster kinetics of the persulfate. This works in the case of the Bailin landfill because you have a layer with a very short amplitude, not a very extensive, relatively well-controlled layer. If we were in a more dispersed aquifer, a more extensive aquifer, Sardas, for example, then we need to approach the thing differently and think about other strategies. In the case of Sardas, we are thinking about creating biological barriers, for example. But the first goal is always the dense phase, the DNAPL. Okay, we will finalize the round of questions here. So we are going to explain now the phase 2 of the test, and then we will, well, it's going to be Mr. Fernández, and then Mr. Sanchez-Yepes will speak about the contaminated emulsion treatment by adsorption in GIC and adsorbent regeneration, and then we will have Herranz, Mr. Herranz, who will speak on site remediation of fluids extracted in SEAR treatment in the life surfing project at Bailin, and on-site alkaline hydrolysis of fluids extracted in SEAR treatment in the life surfing project at Bailin. And then finally, we will have a video by Fabian Simon and a discussion. So please come to the stage. You have to stick to the time and speak clearly and not too fast to facilitate the work of the interpreters. Thank you. Jesus, you have the floor. Jesus Fernández. Hello. Hello again. I think it is not necessary to repeat the introduction because I hope that it was clear before. So let's finish with the last chapter of this first part of the test, which is the in situ chemical oxidation enhancer, and has with surfactants in a fractured aquifer. So we injected oxidant active with soda in the fractures. Once we ended the injections in the 2 tests in the cell, we made a dosage with smaller flows to upstream, and then downstream we introduced barrier generating foams to minimize the flow downstream and to increase the contact time in the cell. And we maintained the alkaline hydrolysis and aeration treatments. In the barrier zone, it is there's no reason to use oxidants because we are going to inject oxidants in the cell. As for goals, as in the previous case, we wanted to reach the target level at a residence and the residence time of several hours in the phreatic level. And although the persulfate kinetics is slower in this heterogeneous medium with fast circulation, it's meaningless to have more contact time as an oxidant solution. We had a mixture with emulse, 4 grams per liter or 5 grams per liter, depending on the amount. As for the persulfate, we worked with 4 grams per liter. Sorry, the emulse as an oxidant solution is 4, not 5, 4 grams per liter, and the emulse in the foam solution is 5 grams per liter. We injected 20 cubic meters for 2 days. As for the persulfate, it was 40 grams per liter, and the target was to reach a pH of 12. In the foam solution, we mixed the emulse, 5 grams per liter, as I just said, with xanthan gum, 2 grams per liter, in a volume of 2 cubic meters for 48 hours. We have manual probes, fixed probes, in fact, to see the evolution of the plume advance, and we wanted to also see the arrival time and the dispersion rates. As for the SISCO injection, 1 meter cubic at the highest flow possible so that the level is recuperated and then you inject another pulse. The goal of this is to achieve more dispersal of oxidizers. The recirculation, as for the recirculation, we had some problems on the lower part. You can see the blue line with the performance of recirculation, relatively low performance or poor performance because of the complexity of this medium. If you use with pneumatic pumps, flows are too low. If you use the electric pump, then it is so fast that it exhausts the well and does not allow for continuous operation. So it's just necessary to obtain a system with electric pump and a variator to adjust pumping flow rates and work continuously. We used a micro-perforated tube or hose, if you want, like the ones that are used for irrigation. And the foam was only generated above the phreatic level when aeration was initiated. We did not carry out previous tests, and we created a good amount of foam over the phreatic or above the phreatic level. As said, we had an aqueous solution with 2 grams per liter of xanthan-gum and 5 grams per liter of emulsion, as I told you before. And as for the aeration, we used a field compressor, plant compressor, diffuser through this micro-perforated hose or pipe, 11 meters long. Along the layer, you have different boreholes, and the performance of the level in the test area, the level in the borehole is 196. You see that the response is practically immediate after each injection pulse, and we got to the goal threshold at 110, and the pumping in the third graph, you can see that it was not efficient because we need these peaks downwards sometimes. And what we observe downstream is that this injection in 2-3 moments when using pulses is being decreased, and downstream or we have downstream we have a single plume. We have probes close to the barrier zone where you can see there is an important increase of the phreatic level without any recovery, any decrease. And therefore we are at a situation of filling up the boreholes with a bad communication. How contaminants have evolved in the area where we injected, we see that there's a good solubilization thanks to the surfactant, and it is kept along the M layer close to the barrier zone because we have still dense phase in the P195 and in the P198. These are the names of the boreholes. And the persulfate, you can see that it is kept with relatively high concentrations in all the layer up to the barrier zone. However, we see that the surfactant is decreasing due to adsorption along the layer, but also due to degradation, due to the oxidation by the persulfate, and also because of the alkaline hydrolysis reaction. As for the evolution of compounds, you see that at the beginning, the concentrations of NACs, that is the heavier or heaviest contaminants, are more important that at the beginning, and then you see how the chlorinated compounds decrease up to almost 0. However, you see in the peaks that the concentrations are still kept at rather high levels. If we move downstream, you see how the POPs are, sorry, the COCs are going down, and the persulfate, and we see the same situation as in the barrier zone SEAR treatment. The moment we lose the objective pH, the persulfate is kept because it is not depleted, only because of that. As for reagents and components along the layer, here you see 2D representations considering time and distance to the boreholes, you see that the pH has been maintained at suitable conditions along the layer to favor alkaline hydrolysis and persulfate activation during most of the test. The persulfate maintained significant concentrations for the first 4 days, reaching concentrations of more than 5 grams per liter up to borehole P222. The persulfate has accumulated in the wells in zones of very slow communication, functioning as continuous tanks until the exhaustion of the persulfate. You see here that it is the surfactant concentration decreases by diffusion, absorption, and reaction with PS. In the test cell, the presence of surfactant has been maintained for some time in the dead zone of the boreholes until its degradation by the persulfate. The sum of contaminants or COCs. What we see is solubilization due to the emulse contribution. So it increases above the baseline level, reaching peak concentrations of 1 gram per liter in the boreholes where the DNAPL still remains. In the barrier zone, the increase over the initial concentration is negligible. Upstream of the barrier zone, the concentration decreases progressively due to the processes of alkaline hydrolysis and oxidation by persulfate. As for the contaminant evolution, you see what we already said. We see that the contaminants that are heavier, more than 5 chlorides, before the test area and up to the barrier zone, you see the initial increase of concentrations while the surfactant is still active. And at a certain point, it decreases due to the effectiveness of alkaline hydrolysis and the oxidation with persulfate. Just to see the evolution of the contaminants, if we compare with the distribution of contaminants in the dense phase, which would be the left-hand side bars, you see that the participation in percentage is the most heavy chlorides, hepta-CH, hexa-CX, with a very high percentage in DNAPLs at pH 7. They almost disappear in the solubilization of DNAPLs under alkaline conditions. The hydrodechlorination kinetics is very fast for these two compounds. You see here in P55, there is still DNAPL at the beginning. The first hours, you see relatively high concentrations of chloride compounds, the heavier chloride compounds, and how you see how over time they decrease, and downstream in the case of P79, you see after 4 days, the heaviest chloride compounds disappear or practically disappear. As for the lighter chloride compounds, we observe that they advance a little bit more than the heavier chlorides, and they are kept in the probes and they are functioning or working as if it was a test. We observe an important generation and rapid generation of trichlorobenzenes, TCBs, and tetra-CBs, which continues in the cell until the precursors disappear. We were not able to find this in the literature or in the laboratory. In fact, in order to see the performances obtained, as we presented in the case of the surfactant, we suppose that the volume injected, because in this case there is no recuperation or recovery, it is a rather conservative volume. I mean, in the section of the layer where the volumes are conservative, we can assume that the level rise is proportional to the flow rate passing through a given point. So the total volume, the injected one, will be the sum of the flow rates passing at each moment. Moreover, Taking into account the analysis over time at these points, we can consider that the mass at each moment will be equal to the flow rate and the concentrations at that time, and the sum of these masses will be the total mass that has passed through a given point. Below the base level, the aquifer behaves like a discontinuous reactor and evolves according to the persulfate mass, pH, and COC's concentration. Therefore, the estimate of the mass circulating through each borehole is a downward approximation. We see that we have solubilized and degraded between 12 and 17 kilos of solubilized COCs or contaminants. As for the conclusions, we've seen that the dosages that we were using were adequate to solubilize the COCs and to degrade them without generating risks. But there is a need to dose these to maintain the objective pHs all along the layer and taking into account the carbonates existing in the aquifer. We also need to improve the barrier zone directly under the test zone, and we use the foam just downstream of the recirculating or recirculation cell, and we needed to improve it through because we have problems upstream because the connection thresholds between siltstones and sandstones are increased, and therefore there are flows that we want to avoid, or leakages if you want. As for kinetics, the heptachlors and the pentachlors indicate that the hydrolysis is really fast, and the kinetics of oxidation by persulfate are slower. They are efficient, but only if the alkaline pH is maintained, degrading the COCs, the contaminants, in approximately 4 days. And it is necessary to add hydrogen peroxide along the layer and over time to maintain the pH at set point conditions, compensating for the tendency to neutrality due to carbonate condition of the aquifer. As for general conclusions, in such a heterogeneous environment, it is feasible to enhance the extraction with surfactants and in the combination with oxidants and surfactants. The selection of reagents, oxidants, surfactants, activators, etc. at laboratory scale is important not only to establish dosages and yields, but also to take into account the compatibility between them. A detailed knowledge of hydrogeological performance is essential so that preliminary strategies and very concrete, very specific strategies can be focused and presented and implemented. We have been working in an area that was some 800 meters from the riverbed, and we had distance enough to the receptor to work and to minimize the contaminant levels. If we were working closer to the river, we should implement measures to slow down the flow or to degrade the contaminants. In the overall pilot test, during the tracer test with the cleaning and the mobilization, we recovered further 100 kilo of dense phase, and therefore in total we removed 240 kilograms of contaminant, counting the SEAR tests and the SISCO test. We don't want to give you the silver bullet formula, let's say, but we wanted to implement a working methodology and a protocol that must be adapted to each case. In principle, this is the end of my presentation. Thank you very much. Thank you very much, Jesus. Now I'm going to give the floor to Mr. Andrés Sánchez, who is going to speak about the active carbon treatment in carbonated emulsions. Andrés, you have the floor. Thank you very much. Okay, thank you very much. I am Andrés Sánchez, a student of doctorate of the Complutense University of Madrid in collaboration with the Proquima research group where I'm developing my thesis. We are going to focus on the treatment of contaminated emulsions through active granular active carbon as part of the LIFE project. Firstly, we established the basis where this research is being supported, as well as the main goals. And continuing with the test carried out, as it has been mentioned, we focus on the waste produced by the Inquinos factory up to 1989. And out of the production, a total of 28 chlorinated organic compounds were created, and we named them DNAPLs, and they were dumped in a non-controlled manner, so that there is a very high contamination. So I'm going to focus on the treatment of the preparatory work, the treatment that has been implemented with the non-ionic surfactant called EMULSION. The SEAR is a treatment injecting surfactant on the soil, so that when we extract the DNAPL, we can decant a part of the DNAPL and get a solution with a solubilized DNAPL. We're going to focus on the treatment of this highly contaminated emulsion, and for this purpose, we propose absorption in a granular active carbon column, obtaining free from NOx effluent, effluent or contaminants effluent, and we will adsorb until we get depleted carbon, and we can either store this carbon or reject it or incinerate it or burn it, but the formation of the creation of toxins would be very important problems, and therefore regeneration is approached. And for this, we will use a persulfate solution activated by temperature, and we will remove the compounds up to the obtention of a totally regenerated carbon that can be used in a future generation cycle. So we use sulfates as the result. In research, we see that it is deposited on the surface of the carbon, and therefore it is necessary to wash the column with water to remove these compounds and to give a new use of adsorption to the carbon. In this implementation of adsorption and regeneration cycles, this is what our work is going to focus. We divide it into two phases, absorption and regeneration. We do it in a lab where we have an activated carbon column with 20 units, and we recirculate carbon for 144 hours, which is the moment when we decide that the column has been already depleted, and therefore we use activation at a temperature of 60 degrees in a heating resistor. The resistance is around the column so that the temperature can be kept, and we are going to monitor the evolution of the process. As for the analysis conducted, the quantification of this is done by surfactant, quantified by titration. The emulsion was characterized, intensified by adding more surfactant and enabled so as to take it to extreme conditions, reaching a concentration of 9 grams per liter of solubilized DNAPL. And you can see the high HCH rate obtained. For the first absorption cycle, we present the concentrations and the equivalence of the material absorbed by carbon. After the process, we see that up to 99% of the chlorinated compounds were recovered, but only 1% of the surfactant, 20% of the surfactant was recovered. Then we conducted the first regeneration cycle, where after moving all the persulfate solution, we obtain a total of 75% or 76% sulfates that were recovered and washed with water. And with this, we implement absorption and regeneration cycles, a total of 3, where the total chlorinated compounds absorbed was constant and over 80% at all times, which is a very favorable piece of data, while the amount of surfactant was decreasing. It is not a negative point, but when increasing the amount of surfactant, this can be used in other treatments. The amount of persulfate was decreasing the more cycles we used, because it was more selective towards the chlorinated compounds. When analyzing the reaction waters and to ensure that we did not have an adsorption problem, less than 1% of those compounds were detected, the COCs, I mean. As for the main conclusions, this process is effective for the treatment of emulsions obtained by from the SEAR treatment, where there is a selectivity in the carbon treatment, and therefore we foster the use of activated carbon and the circular economy in this process. The use of persulfate has been proved efficient and effective when increasing the number of cycles, because the consumption is decreasing, because at every cycle it is necessary to less amount of surfactant is necessary. I will finish my presentation here by acknowledging all these parties, different parties that are paying for my scholarship. Thank you very much. Thank you very much, Andrés. Now, Mr. Carlos Herranz, technician of the surfing project, is going to present. I'm going to load your presentation. Thank you.
So you have 2 presentations, one after the other. I will let you know when the time is up. Okay, first of all, let's remember the different phases. First, the tracers and CR1, 2. We will talk about the liquids extracted by the SEAR phase. It's a highly contaminant emulsion made of the COCs plus C28 types and the surfactant, in this case, EMULSI-3. It is the non-ionic surfactant that was selected. 3 techniques were evaluated: advanced oxidation, activated carbon, and its regeneration and thermal alkaline hydrolysis with aeration. The shared goals are reducing contamination of the emulsion, allowing it to enter the depurifier, and its use on field or in field. First, let's talk about advanced oxidation. The basis is the reaction of oxygen peroxide with the Fe2. So radical hydroxyl is created. This is the one with the surfactant effect. And then we see how it reacts with the other compound that has less reagent power. So in laboratory, it was used with with 3.7 grams per liter of DNAPL solubilized plus 11 grams per liter of emulsi 3. We see here the stoichiometric amounts. So for each 12 moles, we should add 1 mole of COC. Then we analyzed 3 times this emulsion with 50% of a stoichiometric amount, 100% and 200%. Here we see the results. We see first conversion of contaminants below 80% in 144 hours. And then with 100% stoichiometric above 80%, and with 200% higher concentrations in shorter time. So we see how the COC are remaining in the treated sample. At the level of the pilot project, we see a reactor of 300 liters with agitation recirculation, pH control, and slow aeration, but not in the water or aqueous matrix, but just to move the compounds to a chimney of activated carbon that is here. So here you can see a real picture of the reactor with the chimney, the recirculation, and pH control. On this reactor, 200 liters of the emulsion were treated. The amounts here are 90% of stoichiometric needed for the reaction. That means we used less hydrogen peroxide than necessary. So we reduced pH of the reaction to 3.3 because that's where it works much better. The catalyst works better. So after the test, with the agitation, the sample taken at the different hours, the over 72 hours, we saw how with 48 hours, we reached conversions of around 90% due to the oxidant being exhausted or used up. With more, we should have got higher concentrations. With that, we increased the pH to favor oxidation of peroxides. We here see a chart showing the 3 states or phases of the test. We see here how the green bars are the highest ones because regardless of the 95% conversion, the Na or the soda addition also helped. So with per 100 milliliters of the solution, we added DNAPL and we agitated for 24 hours under ultrasound, and the test showed how 9 grams per liter of COCs were retrieved, and with 10 grams of SURFactant. That means that the emulsion is still having certain power, and the advanced oxidation is selective of the COCs. Let's see the next technique, activated carbon and its regeneration, particularly absorption of COCs and surfactant on granular activated carbon and regeneration with TAP. We see here an image of how contamination can be absorbed, not adsorbed, on the pores and the cracks of carbon. The chemical basis is the temperature from 45 degrees transform persulfate to sulfate radical. That's the one with the power, the oxidant power to convert COCs in the regeneration of activated carbon. Here we can see a real picture of the used activated carbon, the one used in the facility in Bailín. And then at the level of the pilot, we have a filter to which we added 250 kilos. In this direction is where we see the washing cycles, absorption of these 250 kilos. Time of residence is 40 minutes. So 30 cycles in 20 hours. Once the absorption is finished, we go to see the regeneration. We install 2 resistances to elevate temperature to 45 degrees and foster regeneration of the sulfate radical for 20 hours of recirculation, and we obtained 40 grams per liter in the solution. That means 75% of the stoichiometric to be able to eliminate all the COCs. Once we finish with this regeneration phase, we have to dry the filter, eliminate sulfates, fraction it in different sections, homogenize and analyze. To summarize this information, at the level of the laboratory, we know now the concentrations of saturation of the contaminants. In the case of COCs, 120 and 160 for the surfactant. Absorption and generation cycles happen, so we recover 80% of absorption capacity of the GAC, and we also see how more and more persulfate is recovered less and less. That means that there is a possibility of solubilization or solubilization. About the pilot test, we adsorbed 99%. Why? Because we were in situations below saturation. After regeneration with the 500 liters, we saw that there was a 30% of contamination retained in the carbon. That means, or that is because we used persulfate in a short amount, and we also saw there is an unproductive amount in carbon that reduced our performance. Despite all this, we see here milligrams per liter in contaminant in all the cylinder, depending on the situation. This is how fluids were drained to section number 4. More exhausted reagents were arriving. Also, migration of more volatile compounds in this section. To summarize some information, both techniques are used for emulsion for different goals. Now, the recipe in the case of advanced oxidation is stoichiometric with 95% conversion around 24 hours. But in the case of activated carbon, adsorptions of 99% with a recovery of up to 80%. And remember, there is certain unproductive consumption of persulfate. So we are at the point where we should improve operation conditions and optimize economic costs and treatments of this design. And with this is, this is the summary of the 2 techniques. Let's remember we have 3 techniques. We treated fluids extracted in the SEAR tests, but in this case we will talk about the alkaline hydrolysis on fluids, the same objective, to reduce contaminants and their reuse. The technique means or is thermal alkaline hydrolysis with soda and temperature enhanced with air steam for dragging volatile COCs with pH over 12. There is a dehydrochlorination. together with temperature that increases volatility of COCs. At the laboratory level, we studied and showed certain routes. So after a first soda attack, there are certain compounds being created. So in the case of isomers SCH, there are trichlorobenzene, and also in the case of the dichlorobenzenes. But in the cases epta and hexa, there are tetrachlorobenzenes. About maintaining these alkaline conditions that allows us for the breakage of the molecules, making them lighter, less toxic, and also increasing their volatility, reaching even total mineralization. That would be the ideal situation or result. After laboratory test, we took this to the double chamber situation in the pilot plant with a recirculation, adding anti-foam soda to generate foams, and also the fluid dragging to take all this to the two filters. Here we can see a real image of the reactor on site, built for this test with the resistances and the volume, how the diffusers are inside, and also the spray system for water recirculation. The exit, the two, as I said before, filters or GAC, and the points for the sample taking. With this reactor, 3 tests were carried out in 3 different dates, in similar conditions, with different volumes in different concentrations, but in all of them, we looked for the same, to keep the same temperature of the resistances, and the point of 12 as a target point, 12 pH. Main difference is that in test number 1, we added manually soda, and in the other, it was added automatically. If we see the consumed volumes of the soda, we saw an considerable increase in the other two due to failures in the automatism. More soda than needed was being added, but that in any case meant no disadvantage for the test, or only in the side or in terms of costs. Here we see the performance of the 3 tests with the 3 different sample points. We can highlight that just with 6.75 hours, we eliminated 99%, 99.5% of and we used all the emulsion, but in test number 2, we needed more hours for the same percentage of HCH, and 48 hours in the case of emulsions. If we go back, we see here that the charge or the load of a SEAR extraction was much more contaminated than in the one in test 1. Also in test 3, there was more amount of emulsion. It means we need 21 hours to eliminate all the emulsion. With the hydrolysis, we really destroy all the emulsion. Here we can see a summary of the end of the 3 tests. So the average was a conversion of 94% of all the contamination. About this test, the norm would be, or the formula would be 45% and pH 12. That means degrading all the CHC lindane are more quickly destroyed than COCs that would need more time, due to the top pH that is left in the residual water that could be reused on field, but not with surfactant properties, but with hydrochlorination properties. About aeration, this fosters the reduction of aqueous matrix of CLF and VOL of aqueous matrix, and also about cost, a lot of electrical consumption. So we need to improve the design of this reactor to get a better isolation and to reduce electric consumption. And last but not least, would just go over the three techniques. The three techniques are used to treat emulsion resulting from SEAR techniques. So in the case of reducing contamination, they can be used, the three of them. In the case of the first two, they have surfactant properties. I mean, both advanced oxidation and activated carbon and its regeneration. In the case of activated carbon, the formula would be this stoichiometric amount with the peroxide and reaching conversion of 95% in 48 hours. In the case of activated carbon, if we are above saturation, 99% of adsorption and recovery of 80% of GACs, and degradation of 94% at 45% in the case of thermal alkaline hydrolysis. With these, it would be all. These are the reference we use to establish the root breakage of molecules with the hydrolysis. Thank you very much. I will just allow this question, and you can decide who's going to answer. Of these three on-site technologies you showed us, you selected which is the one that would be more appropriate to the treatment of the fluids extracted in the SEAR? Well, I have my conclusion that would be hydrolysis, because I think reagents are cheaper. It is not as complex as the Fenton, for instance. And in the case of activated carbon, is that it can be regenerated, so you don't need to take out contamination, but you can play, so to say, with the persulfate amount. I would just say hydrolysis. Can you hear me? Yes. Well, in Santos, we replicated the hydrolysis equipment with some improvements. In the case of activated carbon, it is, so to say, a safety solution, because we know it works. We also thought about using activated carbon not as a laser adsorbent, but in a future project of restoration of the landfill of Bailin, that right now is like a nude rock with contamination. The idea is to generate technosols to cover the landfill at the same time as we decontaminate the rock. So this activated carbon would be a regulator for decontamination, so that the microbiological treatment would be more efficient. Another question. We saw how the execution of this live surfing test was carried out in a particular area of the old site. We saw that there are also DNAPL in other areas of the landfill. Could you specify where, and if you're going to use this test or this technique? Well, the idea, seeing that it works, is to replicate it to those layers with DNAPL in Bailin. We only have one doubt in the layer M. We have a lack of information of data between the two zones, and because we lack information about the fluids moving, we don't really know where the fluids are moving. These are boreholes that might not be connected or communicated. So we need to clarify this. We have two options: permeabilization or or waterproofing. We need to select whether waterproof or not, and keep on working on those areas, sorry. More questions from the audience? In the preparation stage, I understand tests were carried out with different surfactants, different mixes. Jesus mentioned how important it is to take into account the compatibility of the agents. I was wondering, were you able to identify whether surfactant was partially oxidated, and more particularly in the case of pearl sulfate and the selected anionic surfactant? Well, about the analysis of the type of surfactant, that's been going on for some time now. The first ones were started in 2009, 2010, comparing 40 mixtures of different surfactants. Initially, our goal was to solubilize, not to mobilize. Then we looked for just the opposite, a surfactant that was able to change or modify the viscosity characteristics. And for this case of life, we selected what were initially shown as properties in both senses, as a solvent and also as mobilizers. We opted for emulsion because not just the consumption was low, it also works on alkaline pHs. It even increases solubilities with alkaline pHs, where in the case of others is not the case. Apart from that, it is biodegradable. And also it is easy to get to particular amounts. So emulsion really makes us easy, and it has a very nice smell.
Pavel Hrabák, Technical University of Liberec, Czech Republic. I would like to ask you on polychlorinated dioxins, since they are known byproducts or impurities of hydrolysis of HCH. Could you comment on that, if you have followed them or monitored if they were present during the process? Thank you.
We never contemplated dioxins in this case. In the case of this test, we analyzed and monitored dioxins in different matrices. In the matrix, water concentrations are below detection levels because they stabilize not very well. But in solid residue, there is a presence of dioxins in all sorts of residues, and there is an increasing concentration of dioxins as we enrich, as we separate the concentrations of alpha, and we move along the isomer. So the concentration of dioxins increases when isomers are heavier and there are other compounds. So the more concentration of dioxins is in the dense phase with around 35,000 nanograms. In fact, it is obvious that dioxins are generated per Photochlorination of lindane at temperatures not above 80%, 80 degrees. I have a question for Andres. Sulfate recovered in the process of the regeneration of activated carbon. What do you do with them? Do you convert them in persulfate? No, they are considered as waste water. That's why we're trying to quantify the recovered amount. There is no treatment done to them. You want to value them or valorize them? That could be an option, but so far it's not being considered. Thank you so much. Okay, if there are no more questions, let's have a look. Let's watch the trial video.
The Life Surfing Project is a European project funded by EU Life Funds. We are 5 partners participating in the project: the Government of Aragon, which is the coordinating partner, plus SARGA, the Complutense University of Madrid, the University of Stuttgart, and the IHPA, the International Association dealing with HCH and pesticides. We're currently executing the in situ test in the old cell of the old Bailin landfill. The test is made up of 3 phases. The first one was carried out in May-June 2022, injecting a solution with SURFactants in order to attack the dense phase and to extract most of the dense phase remaining in the landfill rock. We extracted that solution and we treated it on site, and currently we're executing phase 2 on site, what we call the SISCO, where we are going to inject a solution of water plus surfactants, which are a sort of industrial soaps and oxidizing agents, in order to treat on site the dense phase that is still remaining in the most inert part of the landfill rock that didn't disappear during the first phase. Our intention is to carry out this test on site throughout a week. 1994. What we constantly do is we check how levels are progressing within the cell being tested while our colleagues are injecting the reagent to clean. This is done so as not to exceed certain levels and not to lose reagent. 23.7067. What we are doing here is in a 12 cubic meter tank, the one you see behind, we prepare a mixture containing the oxidizing agent or oxidant, which is persulfate, the activating agent or activator, that is soda, and the surfactant called EMULSION, or EMULSION, which is biodegradable and non-ionic and therefore do not mean a risk when being injected in the soil. We are controlling the injection flows into boreholes in order to first increase phreatic levels up to a certain value. There is a foam barrier in a subsequent borehole, and when that level is reached, we stop injecting. Then the already injected persulfate reacts with the contaminants present in the underground water, subsoil, for a period of time enough to remove the toxic compounds or to transform them into more biodegradable compounds. We measure levels, we measure pH, conductivities, dissolved contaminants, etc. When we add a surfactant together with the oxidant, we also improve the solubilization of the organic compounds that are strongly adhered or attached to the surface of fractures so that we can oxidize them more easily in the aqueous phase. There is no risk of contamination flowing downstream because we are controlling both the dosage of EMULSION or EMULSION, the soda persulfate, so that we don't have a high increase of contaminants in the aqueous phase. And we are also implementing actions in the barrier zone so that if some contamination flows down, through the addition of alkali and the breaking up of the emulsion, we can eliminate the concentration of contaminants in the underground water. We are at the reference laboratory of the government of Aragon. This is the center where some 500 organic compound samples are treated, analyzed monthly, and they are going to be treated in different phases, solid, liquid, etc. We daily analyze the flow samples for a follow-up of the contamination in the baleen and sardas plumes, and also the baleen and sardas treatment plants. In the research works, such as the live test, we analyze the compounds of both solid and aqueous samples. All of them are analyzed with gas chromatography. We extract all the compounds to be treated, and we determine with mass detectors using FIT-ECD for the most concentrated samples. The live surfing project was created as a need to give a solution to the cleaning of the residual dense phase in the baleen landfill. Already 4 years ago, our capacity to extract dense phase through pumping was very limited, and we came to the conclusion that we had to start using chemical reagents to favor this mobilization and the degradation of the potentially remaining material in the aquifer. Baleen has very challenging geological characteristics for any kind of chemical treatment. It is a highly heterogeneous fractured site, which has forced us to make a far greater effort than what was initially planned in the LIFE project. Before applying the reagents, we needed to conduct at least 8 hydrogeological tests and 6 tracer tests to be able to know almost in such a small scale as centimeters where and at what speed were the reagents circulating that we would inject later. In addition, we wanted to guarantee that these reagents would not reach the river, and therefore a great part of the effort was to implement a barrier zone to avoid reagents being injected upstream to move downstream down to the river, by favoring their degradation in a stretch of the river that we have equipped almost at the end of the layer where we carried out our works. Finally, we were able to execute 2 tests with the application of SURFACTANTS and a last test with the application of SURFACTANTS and OXIDANTS. As a result, we have been able to extract more than 200 kilograms of dense phase, and in the last test, in the dissolved phase, we degraded some 20 kilograms of toxic compounds. The outcome tells us that in such heterogeneous contexts, there is no silver bullet that we can extrapolate to other sites, nor even to other parts or our own site, But we have established a methodology that allows us to keep on working with the same reagents up to the cleaning of those areas where there was a dense phase in the baleen landfill. Thank you very much. And now, by way of conclusion of the first block devoted to live surfing, I would like to express 2 conclusions, very general conclusions. I would like to underline the fact that, as we have seen here, the previous works are really important in such difficult context and complex context as this, but they could be extrapolated to simpler sites or simpler environment. The previous tests are fundamental in any case. We need to devote a lot of time and effort and make a very thorough previous work in order to later design the right strategy to be followed in the implementation of the possible or potential solutions. The second general conclusion that is applicable not only to lindane, but any remediation work. As you have observed, a single remediation technique normally is not enough to reach the goals. And therefore, it is normally required to use either consecutive or simultaneous treatment to achieve these goals. And this entails a lot of money, a lot of time, a lot of effort. And this is why we need to place a bet for these research works, in this case, a demonstrative project, such as the live surfing project, which is the only way, in my opinion, to solve many contamination problems that unfortunately happen and will continue to happen, I suppose. Anyway, we conclude this block and we can make the lunch break right now. We'll be back at around 3 o'clock.